All right, so recording.
This?
Yeah.
Yeah.
So, and then we can move this a little bit. There you have that. All right, so I don't have the clicker yet, so we'll have to use the laptop to go through. So at the beginning of every meeting, we'll have like a kind of a question to ponder. So just take a look at this question, talk with your friends, and talk to people next to you. Just kind of get an idea, see what you can come up with for this question. We'll start discussing the answers and stuff in a few minutes. So, yeah, what's up?
Where do I link them so they can get access to the Kaggle stuff? Do I just go on Kaggle?
We can't. Yeah, we're gonna have those links to the
Did you do?
I need.
Do you want to
Yes,
handle?
I need the clicker.
Do you want to handle that when that happens?
Yeah, I'll just come up here and show them where to go. And I'll pull it up.
So that's
Yeah. Yeah. So we because the website redirect is in there.
I can really get
Right. Okay. Well, the redirects are working, but the website isn't. Yeah. And you go through the website to actually get the Kaggle. Yeah.
Let's break things. You know the difference between a development branch and a production branch? Yes. You don't have to do the production branch until it's been validated. Guess what John's done?
All right, let's not talk bad about that.
Okay.
No,
So.
I'm talking bad about him because he's a table stuff. So if you want to restart.
Did you have the clicker?
I mean, we can just edit out the beginning if you really want us to cut it. So it's not a big deal. And you set up the MP4 and everything?
Yeah.
Okay, good.
Oh, perfect. What? Oh, good. Fantastic. Okay.
Shoot quicker.
Yeah. Left, right.
And you have a pointer on it too. Yeah, the markers are here.
I can do a
Yeah.
Oh, I love that.
All right.
Yeah.
So make sure. So this is kind of a bigger room. So
project.
speak up a little. Yeah, project a little bit. I don't think there's a microphone in this room. So
All right, guys, you have any thoughts on this question to ponder? What do you guys think? How do we do this? We have all this data. We need to figure out what's happening in the data. What do we do? Look for patterns. Yeah, true. That's pretty much what we're doing with models. Anybody else? Yeah?
Format it so it's easier to look at.
Format it so it's easier to look at. That's definitely a good starting point. What about Jarvis? Yeah?
Load into an Excel spreadsheet.
Some might say that's the right answer. Yeah. So there are all sorts of ways we can get information out of data. This club, we're going to go through weeks of different lectures on models, different ways to extract useful information from data, because we're not just trying to extract anything. We need to have something that we can apply to the real world, have something that can help whoever we're making the model for. So this lecture is on regression. It's one of the more it's more of a foundational statistical concept that's related to machine learning, not necessarily going all the way to machine learning, but we're going to try to tie it together. Have any of you guys taken like Stat 1, Stat 2? Yeah? Stat 3? Hey, me too. Yeah, regression analysis. So yeah, regression is covered in all those classes. We're not going to go super deep into stats in our lecture, but what we are going to do is we're going to kind of relate regression to machine learning, to artificial intelligence, and kind of see, where all this modeling starts. So as you can see, artificial intelligence really is just kind of beautifying statistics and putting a nice gold frame around it, and people watching. As I said, it's a good starting point to start at regression. Machine learning kind of uses regression to build bigger models. Learn more about. Oh, my bad, guys. Okay, so what is machine learning? Does anybody have an idea? without kind of just reading this quote? No idea? I guess that's what you're here to learn. So, machine learning algorithms build a mathematical model of sample data, and it's known as our training data, in order to make predictions or decisions without being explicitly programmed to perform the task. So really we're just trying to estimate a function to model the relationship of our training data. This is a little different than traditional modeling. We have this is a traditional kind of way we would reach a response variable y. We could have our x, which is an independent variable. We have our rules or our relationship we kind of believe exists between our independent and our dependent variable. Put it in a black box, which is, a model or whatever you'd like, and we get our response variable y. So how might we change this model if we want to look at this from a machine learning standpoint? Which of these inputs and outputs could we maybe switch? What do you guys think? Any ideas? Yeah? Don't give it as many rules. That's a start, yeah. But rules kind of still needs to factor into this equation somewhere. Yeah?
So the result y doesn't have to go like in a certain direction, maybe it can be multiple directions.
True. Yeah, you could learn more about that, but not quite there yet, yeah?
Maybe you get more rules after you put it in the black box.
Right, that's getting there. What we're gonna do, basically we just switch the y and the rules. We give our data the x and the y. So it has, real world data, an independent variable, a response variable. We've sent it into the black box or our machine learning model, and we gather more information, or we can kind of estimate the relationship between our training data. And if we have good data, well-sampled data, you can in turn estimate the relationship in the real world, in the population. And these rules are not set in stone. We're estimating the rules. We're not necessarily saying that's exactly what's happening. It's all just an estimation, really. Here we have the machine learning feedback loop. What do you guys think is the first step on this loop? What do we need to do before anything else?
Create the model.
Create the model. We'll get there later on. Yeah?
We have to put the data into it.
Yes. We have our data ingest. So we have to get our data. In this club, we're going to be giving you some pretty clean data. You're not going to have to go out there and web scrape for your data for these notebooks. We're gonna be giving them to you. After we've taken in this data, we have to clean it, which is what you guys kind of said as well. Cleaning just kind of goes with, we kind of just standardize the data we have. For instance, there might be some outliers or some mistyped, misinputted data that we have to kind of work through. Here we've got an example of some very noisy data. You see on the ID4, we have an age that is a date, and we have, a string rather than a integer for our monthly income. And these are super common. A data scientist or somebody that works with data a lot, this is the majority of what they're doing. They're cleaning their data because your model can only be as good as the data you feed it, right? And oftentimes, the differences in these Kaggle competitions is how well they clean the data or how well they engineered features from that data. And by features, I just mean kind of ways to change your data or transform your data to learn more about the relationships within it. And part of that cleaning process is the train and test split. So here we have our full data set, and we're only taking maybe, in this example, a fifth a fifth of our data set for our test data, and we put that completely aside and put it in a drawer and don't touch it until later on in this process. Then we have our training set and our validation set as well, which we will use in our modeling and our training process. What do you guys think the purpose of this is? Like, why might we need to split this data up before we can work with it? Because it's out of control. What do you mean? To have control. Right. Have control over.
No, like an experiment, you want to have a control test so you can test your data.
Yes. Right. The test set does kind of act not necessarily as a control, but as a way to diagnose our model down the road. We want to learn, or we want to use the training set and the validation set during our training. The validation set kind of makes sure that we're training in the right directions, and it like validates or verifies our results during training. But this split is going to show up throughout the lectures, throughout the notebooks. It's really a quintessential part of data cleaning. Nothing too hard, just a few lines of code. So next, we get to the fun part that everybody loves, the model training part. So in this class, we're going to use, or not class, this is a lot more fun than a class, hopefully. In this club, we're going to use Python and Scikitlearn to do a lot of these models. You'll do that today in the notebook a bit. But really all we're doing during the training part is we're taking that training set and the validation set. We're giving it to whatever model, and it continuously tries to improve or tune our model to better model the relationship of the data that we give it. And once we've done that training, we can reach the testing stage. And during testing, like you said in the back, we have to use that test set as a way of diagnosing and figuring out if our model is actually working for a generalized population rather than just fitting to our training data. And this is a problem that all models have, and data scientists and AI researchers really have to focus on is that overfitting problem. Does anybody kind of know what overfitting is already? Yeah?
It's like when you memorize the answers for a test instead of actually knowing how to solve problems.
That's a very good analogy. I like that. So here's our kind of overfitting slide. Which one of these models, they're all on the same data, which one do you think is overfitting to the data? Third one? Why? Too precise? Right, there's barely any error. It's kind of just following the lines like a connect the dots or something, right? And which one do you guys think is underfitting? Probably get this one on the left. We're using a model that it doesn't really follow the shape of the data, right? It is regression, right? We're taking the data and we're saying we want to map a line of best fit through it, but it doesn't really follow the shape. So the model it underrepresents what's actually happening. You can kind of just tell visually, right? You can tell that it's underfitting. Ooh. But the way that we would kind of do this computationally, imagine that on the underfitting graph, you use the line as your x-axis, and you could kind of see your residual plot. I'll make it really big. You can kind of see your residual plot. And it kind of changed, like, residual meaning the error that each point is to the line or is to the model. And if there's any sort of pattern, in this error, we know that we haven't really generalized for a whole population. Yeah.
What do you mean by a whole population?
Right. So our data is from a sample, or our data is a sample from a population, and a good model is one that uses that sample to figure out more about the population, not to figure out more about the sample. Right. So we have to use our data to generalize just right a model that has kind of random error over time, right? Or over our x-axis. There isn't any point on that middle model that there's like certain points that are super far from that line, certain points that are really tight to it. It's kind of constant throughout the model. Kind of has a constant error as it goes. And that's our Goldilocks model. So once we've diagnosed our overfitting or underfitting, you know, we might go back to that training part of this loop. Might try different models. You can kind of get stuck in that training and testing part of the loop for as long as you'd like, really, refining your model. And in the real world, we might move to deployment next, which would be, say, Google has a autocomplete AI that they are trying to optimize. They would deploy it, and then the loop would restart, and they would gather more data from users that are using their autocomplete function. They could train new models. They could learn. They could deploy autocomplete round 2, and it just, as you make a model, you can then start your loop, gather more data from your users, and it really is a slippery slope of data. So what does linear regression look like? That. This is a decent model. You see, there are there's some points that have some high error values, aren't really hugging that line super close. But really all it is the geometric line of best fit through our data. You can really just bake it all the way down to geometry. We have all these data points. We need to map the line of best fit through it. And that geometric point of view is more of the stats point of view. And as we continue, we're going to kind of go more into that machine learning point of view, where you can kind of tweak your parameters and get to the right model that way. So some assumptions before you do regression. Your model has to have some sort of linear relationship. So we kind of saw in the overfitting slide that this model doesn't really have a linear relationship, but we're trying to fit a line to it. You can do that, but it's not necessarily going to be the right model. And what these assumptions do, they help us to ensure that we're using the right model, and they help us know that we can trust our results at the end, or as we continue to refine and diagnose the model. Another assumption we have is constant variance. Anybody have any sort of idea what that might mean in this domain? Yeah?
Is that another word for the random error that you mentioned earlier?
Yeah. And when we say constant variance, we want there to be about the same amount of error over our entire x-axis. Like we don't want certain spots to have more error. And our independence of observations we don't want one data point and its values to directly affect another data point. So say you're getting ice cream with your friends and they get chocolate and you don't want to get the same thing as them, so you get vanilla. Your decision is dependent on them. So here we have another set of points, and there does seem to be some sort of linear relationship, right? Like you kind of see that positive relationship mapped out with that green line. But which of these assumptions doesn't hold? Constant variance. As our x increases, the tendency of our data to be close to our data diverges from our central tendency. So error increases as x increases. And like I said before, you could try to model this with linear regression, but you might want to try to do maybe some transformations on your data, introduce some new functions into your data, because if you have this non-constant variance, you have a changing variance. It's hard to really trust your model as you're using it. No good. So I'm sure you guys all recognize the y equals mx plus b. Nothing new really on this slide. But really, the x and the y are our points in that little black box image that we have earlier. So we know the x and the y in this case. M and b are the only parameters that we don't know. And the m and the b are going to be our tuning parameters. So we want our model to kind of adjust these values as it trains, and it adjusts the values to get to and it adjusts them according to the error of our model. And you're going to see that on this next slide. Oh, you're not going to see it on this next slide. When I say error, I mean that distance from our estimation. And I'm sure you guys have figured out m is the slope, b is the y-intercept. So here's our linear error function. This is one way we could kind of measure how good or how bad a model is. What we have here is a sigma, or a big E, as I like to call it. The sigma is a summation, so we're summing up the distance, the absolute distance of our points of our actual data minus our modeled data. So the y represents the actual data that we give our function, and the y hat is going to represent our estimated y, and the difference of those two represents our total error. And if we sum that for all of our points in our model, and then we divide by the number of points that we have, we get our standardized linear error. Do you guys like this error function, or do you guys think there could be maybe a different way to find an error that might be a little more helpful? No? Anybody know? No? No? Yes. Here it is. Now you know. This is a much more popular error function. It's used more in industry. A lot of the same components as our other error function. However, we're taking our y from our data, we're subtracting it from our model, and then we're squaring that term. What do you guys think that square, like why is that important to square that term? Yeah?
It makes the big differences between y and y hat bigger, and the small differences between y and y hat smaller.
Right. It scales the difference if you have an error that is really big. It'll penalize your model more. And if you have an error that is small, it won't penalize your model as much. So for instance, if you take a point that's near like x equals 200, and it has that huge error, you don't want that, right? So it's gonna say that is that distance squared, and a lot bigger than just that linear distance, right? But if you have a point near like x equals 10, that is real close to the line, that error won't matter as much because there is, like, we accept that there's going to be noise and we want a generalized model, so we don't want to overfit. So we kind of accept that we might have a little bit of small error, but we really want to penalize the large error. So here's the slide I was referencing earlier when I was kind of moving my hand around. We see that we have those two tuning parameters kind of changing, and as they're changing, our line is changing with them, right? So it's kind of doing this stepwise motion, and like, what do you guys think is happening here?
It's putting in random values, and as the difference gets smaller, it tends to favor that more.
Right.
Until it gets to the closest answer.
And it might start at a random value, but it doesn't necessarily continue putting in random values. Like you see when it starts kind of at a negative correlation, right? And it measures the error. It measures the error when it starts at that step, and it corrects the parameters to try to get closer to try to get to a minimal error or a lesser error. And it keeps correcting, and it might overshoot, but it'll converge to the line of best fit. So like I said before, we have that geometric route to getting to this line of best fit by just doing some math on all of the coordinates, but we also have this stepwise, more machine learning based route to getting to the line of best fit, which has to do with tuning those parameters, checking the error, changing your line, checking the error, changing. And this could be viewed as a gradient descent. I know that word sounds kind of intimidating, but all gradient descent kind of is. We can picture this as our error plane, or our plane of all possible functions, and then the error of that function is mapped on top of that plane. So the red points on this graph would represent the places where the parameters have a high error value. The darkest blue would represent where they have a lower error value. So we can look at, so this theta naught and theta 1 would represent our tuning parameters in this case. So say like you want to start with 0.8 for your slope and 0.4 for your intercept. So we might start at this point right here. I'll do it over here now. And then we see that we have a good amount of error here, and we step down and we have less error with different parameters. So we say, okay, we have less error, let's keep walking in that direction. And it keeps going down, keeps going down. And we reach this point where everywhere around it has a greater error than it does. So we know that if all these values around the parameter have a greater error, we have reached a local minimum. However, even if we reach this local minimum, that's not necessarily the absolute minimum. And you guys kind of see why that is. If we're using these steps, these are kind of discrete steps to get to this point. And we have no way of knowing that this is even over here. What could we do to maybe try to detect that? Yeah?
Smaller steps.
We could use smaller steps or bigger steps, but yeah, we could change our learning rate. Yeah?
We can also start in a different spot.
We could start in a different spot. And all these things, yeah, like we would do those things if we're really trying to find the absolute minimum. But in this plane, we really don't have a way of knowing that we've reached an absolute minimum. We only can know that we've reached a local minimum. And you can't really tell if it's absolute because this is a continuous plane. So there's a continuous number or an infinite number of points you can really choose from. So you never really know if you've reached that absolute minimum, and you could kind of view that as a, just something to consider, think about as you maybe use a gradient descent model. But I like what you said about the steps. That's definitely going to be important. So correlation does not mean causation, and I'm going to explain to you why that is with a fun slide or a fun website. So here we have U.S. spending on science, space, and technology correlates with suicides by hanging, strangulation, and suffocation. And that's a pretty tight correlation, right? Like R squared, which is like a correlation coefficient. What are we at? Like 0.99? Like it's almost an exact correlation, right? Number of people who drowned by falling into a pool correlates with the films that Nick Cage appeared in. So people are more likely to jump in their pool and drown if Nicolas Cage is in more movies. Number of people who died by becoming tangled in their bed sheets correlates with the per capita cheese consumption. So you see all these things not necessarily related. Divorce rate in Maine, consumption of margarine. And really, if you think about the world, there's all this data out there, and something's bound to correlate with something else. It's really those meaningful correlations, and not saying that this isn't meaningful, but that you want to look at more. Now let me get back to the slides. Oh. Sorry, it's on full screen. Okay. And this little comic. I used to think correlation implied causation. Then I took a stat class, and now I don't. Sounds like the class helped. Well, it maybe helped, because correlation doesn't always. I think it's a good joke. I think it's all right.
You can press function F11.
Got you. So there are limitations to regression, even though I've kind of hyped it up this whole time. Doesn't perform well with non-continuous predictors. So say that you wanted to measure how many hours somebody spends on homework, and your input data is whether they're a sophomore, a junior, or a senior, or a freshman. That isn't a continuous value, so it's going to be hard to kind of. You could do that, and you could use say like indicator variables that are 1 if they're a freshman, 1 if they're a sophomore. Like there are ways to work around it, but linear regression isn't necessarily the right model to choose if you have a lot of non-continuous data, discrete data. Bad at predicting for binary. So if you want to predict whether or not you're going to pass a test, using regression is probably not the best. 'Cause that's a yes or no, pass fail. Data could also have a non-linear pattern. So we kind of went over this earlier. If you have data that has a pattern like this, a straight line probably isn't going to be the best at letting you know what's going on. Now, given there are ways that we can model curved data by using transformations, and data transformations, all that is say we have these points. If we want to transform our x, we would take a point. We would take each of these points, and we would do log of x on it, or x to the second, or we would do some sort of math function, exponential, log, there's all sorts of different transformations you can try, but really what you're trying to do is move that data into a straight line so you could regress on it. Also, if you have a nonlinear pattern, you could just throw regression out the door and use a different model or a different regression model. And we're going to start talking about logistic regression now. So this is the sigmoid, very curvy, very sexy. 0 to 1 is our range of points that this graph could be. What might that 0 to 1 continue? Like, why might that matter? It's a continuous plane. Graph 0 to 1. What could we use that for? What sort of situations might we want to? Yeah.
Decision makes systems like you want to have some like 0 or 1 decision.
Yes. Just like a binary sort of decision that's either yes or no, pass or fail, something like that. And this 0 to 1 might represent like the odds of you passing, the probability that you're going to pass, or the probability that you're going to fail. And you can kind of use this continuous space as a way of transforming that binary pass-fail into a continuous probability distribution. You can kind of see that on here as well. The upper red half represents our y equals 1. Lower blue half represents our y equals 0. It's kind of those binary responses represented with this curve. And that's really what logistic regression is about. It's about these binary response variables and using regression to figure out the odds, using the regression and the odds of those events happening as your continuous value to regress on. So there's the function form of that graph of the sigmoid. And just as I was kind of talking about the transformations earlier, we're doing a log transform on the odds of success versus the odds of failure. And that log transform gives us that continuous space, gives us this sigmoid-like graph that we can use in our regression. And if you think back to the black box, it did have x and y as the input. We're kind of modifying that y input for this model. And we're using like the log odds of y given x, because that odds has to be a continuous value, right? Or it has to be in a continuous space, given that it has to do with probability. So this is where your mind gets blown. I know it's not, you might not expect that from this weird looking equation, but it's just linear regression. Like if you put the log odds as your y, your tuning parameters and your predictors pop right out, and it looks just like linear regression, right? And that's really all logistic regression is. It's changing your data into a probabilistic nature so that you can use literally just linear regression on it. So I set up this little thought experiment. We're going to let L be the odds of crashing an electric spin scooter. We're going to let X1 be the average speed of the scooter driver. So that's a continuous speed. It could be 15.5 miles per hour. And we're going to let X2 equal 1 if it's the driver's first time on a scooter, and 0 if it's not their first time and they're an experienced rider. And really, we could just tune those parameters. Our intercept, our beta 1, which corresponds with the average speed, and our beta 2, which corresponds with the first time factor. We tune those parameters in the same way as that gradient descent model earlier, and try to get to a line of best fit, but instead of a y, we're using that sigma function and that log odds. And you can see we're using a binary value as one of our predictors, which I said was kind of difficult for regression to do earlier. But logistic regression kind of opens up those doors to more categorical data. And I'm sure there is some sort of relationship between odds of crashing and people's first time riding those scooters. So next time you're out on campus, you might want to take these things into account for your own safety. Logistic regression will help save your life, really. Do we have any questions or anybody regressed out? Yeah? Well, Jarvis is going to do an awesome workbook.
Not me yet. Brandon's going to show you all how to get into the notebook.
Okay.
And I'll take it over from there.
And then Jarvis will take over, yes.
Yes.
Yeah, does anybody have any questions? Because, we really encourage you to ask questions, throughout any time, because we're really trying to help you. One question over here.
Yeah.
Sorry, to be honest with you, I don't understand the relationship between the log and the function you had earlier.
Mm-hmm.
Would you mind explaining one more time, please?
Yeah. You want me to explain it with this function?
Yeah, no, just like the relation between those two equations, how it gets to that, and how it transforms to that, basically.
Mm-hmm. So say that you sample 100 people and ask them did they pass the test, did they fail the test? And then you have information about them as well, like how many hours they studied, how many years of experience they have. So you can kind of use the odds of them passing versus the odds of your whole group passing versus the odds of your whole group not passing as your p-values. And a lot of cases that base is going to be e, so it's like the exponential function. And you kind of use the odds given x function to help map out that relationship. It is kind of like a slippery subject, but do you maybe have a better answer for that?
So the relationship between this side to that side?
Mm-hmm.
Ooh. I don't think I can help you there. That's only you, Mike.
There's some awesome proofs that actually get from linear regression to logistic regression. I would definitely.
The right side, which I think is important. The right side more, right?
Yeah. The right
So-
side has the tuning parameters.
So,
that you're actually-
yeah, so really you're asking the why this is true, why this happened. Yeah, so I would definitely look up the proof on this. But yeah, it's a mapping of the probabilities you have is p, and 1 minus p is the probability of 1 minus p would be the probability of that not happening, and then mapping it to a linear relationship of just your inputs and your betas with your two tunable parameters. Yeah.
Thank you, guys.
Mhm.
So, any other questions? Well, let's give Brett a round of applause. Thank you guys. So we're going to be starting our workbook section, which will be coding in Python. So if you would like to go, if you just you're not really interested in doing that, that's perfectly fine. I just wanted to say again, just to go ahead and on our feedback form. So that's going to be, let me write it up here. Markers. So it's just going to be ucfai.org/feedback.
Hey, Brandon.
Yes.
It's at the end of the slide deck, too.
Is it? I think you put it in. It was after the question slide.
Yeah.
All right. There we go. Sorry. Yeah, so that's that up there. I'll write it up. I'm already writing this. Yeah. So otherwise, you can wait until the end of the workshop to do that. So. All right. So yeah. So if you have a laptop, please pull that out now. You can do this on your phone, but it's kind of annoying on your phone to go through that on Kaggle. So let me pull this up here. So if all of you can go to the Discord, I actually posted the link right to the notebook in the announcements for Core. So that's the easiest way. Otherwise, I'm going to show you just how to just go for it from here. So let's exit this out. And make sure OBS is still working here. All right, so we'll make this a little bit bigger. All right, so so if you want to go to Discord, the link's right there. It'll pull you right to the notebook. Otherwise, I'm going to follow through how to do this now. So first, we're going to go to Kaggle.com. So Kaggle is a website that will host all of our notebooks on. So it provides us the same environment for every person, so we don't have to worry about setting it up on your personal laptop, installing programs. You don't need to do any of that. We can just pull this up online and be able to code and run everything we need to do. And that's all done through Kaggle. So if you haven't already, you're going to need to create a Kaggle account, so you can just use your Google account and just link it. That's the easiest way. Otherwise, you can just go through and create your own account. So let's zoom in a little bit. So the way to do that. So first, we'll bring up if you're not using the link on Discord, we're just going to go to the search bar to search UCF AI bot. So you'll see kind of some of these notebooks come up already. So we're just going to pull up. This is like just like our account we use to host all of our notebooks. So it'll be the first link, AI UCF. You'll see here. Everybody good? Anybody not able to do this? Having issues? Okay, cool. So we'll click that. Bring this up. So you're going to go to kernels. So kernel is just another word for notebook. So just there's what's that word? Synopsis? Whatever. Synonymous. Thank you. So we'll go down here. So the notebook we'll be using today is all the way at the bottom. So Core Spring 20, so SP20, Linear Regression. We shall click that. And there you go. So now this is the notebook. So you're click this button up here, copy and edit, and that will fork the notebook. So basically, you'll get a copy of the notebook on your personal account that you can edit and do whatever you want with, and that's your account. That's your notebook to keep. And then, and it's linked to your account, so you can access it anywhere you log into Kaggle from. Which we're going to need to sign in here so we can pull this up. So I'm going to pull this over here real quick so I can sign in. Did everybody follow that? Any issues? Everybody's got thumbs up for everybody. I got the notebook. Everybody give me a thumbs up. Thumbs down.
When I go to search up AI UCF.
Just search UCF AI bot. Like all one word.
It says organizations are temporarily unavailable.
Do not click the organization. So here, I'll show you. So there's a user and there's the organization. Yeah, Kaggle is under a lot of maintenance. So for organizations. So if you go and do search, you want to search UCF AI bot. And when you search that, it's the first link right here. That's our user account right there. So you want to click that. And then go to kernels, and then we'll be down here at the bottom. We'll scroll all the way down. And it's the last one at the bottom right here, Core SP20 Linear Regression. So we're gonna need Jarvis, you want to come log in on your account here? Because I have two-factor and stuff.
I have two-factor too.
Okay, well you can just log in then. That's your job.
Okay. I told my password though. I don't even remember it.
Well, you're gonna have to figure it out on the spot. All right. So I can walk around and. Well, it's not on the monitor. You're good. Don't do that, please. God.
Please.
All right.
Oh.
So,
That already worked.
He's got to sign in.
No, I'm already signed in.
Okay, so move it over.
So is it this way? Ah, hello.
So,
Oh, it's
all right.
not mine.
Oh, it's signing through you.
That's fine.
Yeah, that's fine.
That'd be
So let me finish that up. So once
Okay.
you have it up here, so this says copy in it since we already opened up, but we're gonna make a new copy. Well, hey. So everybody was able to fork the notebook. We're good to go. Great. So is this good for you for being able to look at it? I know it's kind of small. But.
Yeah, very small, but I will live.
All right.
If I need to, I'll just walk in front.
Yeah. So, all right. So, can everybody read that fine, or make it a little bit bigger, maybe? Let's see. I think that's good. Okay. So once it's loaded up, then you're good to go. So, I'll. Any other issues with getting it set up, I can come over to help. Good. Okay.
Okay.
So I'll leave it up to Jarvis to start it off.
Hello there, guys. So welcome to part 2.
Yeah.
I see you all survived part 1, so congratulations. Give you guys a round of applause. Yeah, it wasn't that bad. Don't you worry. All right. So before we do anything else, we need to do some imports, right? So there we go. Let's make sure this works right quick. Right. So there's a few standard packages that we do import for most data science projects out there. One of the most important ones out there is going to be a thing called NumPy. You might have heard it as NumPy. It's wrong. It's NumPy. Basically, that is the linear algebra library. Another way to think about that, it's just very fancy arrays. So we do a lot of stuff with NumPy. Pandas is a great library for importing data and manipulating data. It also gives you a very easy way to do some basic statistical analysis on your data set without even really doing much. SciPy.stats, that's going to give us some statistics from our data. So kind of more advanced statistics than we'll find in the Pandas library, so we'll get a bit important in that as well. Matplotlib. That is a library that we use for plotting. So if we need to make a graph to see what our data looks like, we're going to be using Matplotlib. And then Scikitlearn, that is the main library we're going to be using, at least for the first 2 lectures, to be making our models. It has a lot of very good and important models in there, and they're very easy to run. So with that being said, scroll down a little farther. So before we get into a proper big data set, we're going to be looking at something kind of basic here. So our basic little data set here is going to be just of some random numbers I generated from the big brain up here. There's obviously a relationship here, right? It's some type of linear relationship. Yeah?
Maybe.
Yeah. I guess my big brain did that by itself. Something like that. Who would have thought? But yeah. So do you guys think we should possibly fit some linear regression line to that? Yeah? All right. Let's see how we do that. So, we're going to show you 2 ways how to do that. One is the hard way, and the second way is the very easy way. So this is the hard way. So we get the number of observations, we take the mean of x and y vector, we calculate cross deviation and deviation about x, we calculate regression coefficients, and then have a variable to set it equal to all that stuff. And then we get our outputs here, right? Those will be our variables that we use for tuning. So, do you guys want to do that every time you make a model? Yay or nay? No? Nay, yeah, that sounds terrible, right? What the bloody hell is all this stuff? I'm a programmer. I want to be lazy, right? And you're just in luck. Programmers out there want to be lazy too. So Scikitlearn came around, and this little thing called linear model. And linear model gives us linear regression, right? So look at that. So we have one line here to define our model. So we say, hey, we want to make a linear regression model. And then this line over here, regress.fit, that's going to take our data and fit our linear regression line to it. So with just those 2 lines, guess what we get? A linear regression model. No nasty maths,
no playing around with code, no double checking work to make sure your maths is right. It's all there, right? And that's pretty awesome, right? Don't you agree? Who likes 50-line code? Who likes 2-line code? Yeah, exactly. There you go. So let's see how well this did, right? So we made our model, and let's plot it out. And oh, look at that. What do you guys say? This model fit pretty well, right? Yes?
Your code to print that out
Mm-hmm.
is not using anything from the model that was generated, it's using all the hand mathematics.
This one right here?
Yep, scroll up a little bit. You're defining y prediction is B0, B1, and B0 and B1
Mm-hmm.
are your hand calculated mathematical formulas.
Yes.
So you're not printing anything from the regression model,
Mhm.
you're printing only the mathematical that we did by hand.
Correct, yes. Yeah, they're going to be equivalent. So if you take, so with Scikitlearn, it's going to be doing the same thing that we did by hand there. So either you could take the Scikitlearn model we generated and find the numbers to plot there, or we could take our handmade stuff and use that to generate it. So you're going to have the same thing happening no matter what. It's just a different way to go about it.
So how do I print out the coefficients from the Scikit model?
So for that, what you'll do is you'll do regress. So that was defined as our model. And then we'll do dot predict. And we're going to give it our x. And then it's going to give us the y's it predicted. And then you use that in replace of y underscore predict. And then you'll get your model that way.
But that only gives me a corresponding y given an x, it doesn't give me the coefficients.
The coefficients, correct. To extract the coefficients, you have to go into the model itself, because it is stored in the model. That's a little more complex and a little beyond the scope of this right now. To plot the stuff in matplotlib, you just need to get points from it that you can then put into your graph there. So you can still get access to those coefficients, but for most applications, you won't need the parameters themselves. You just want to see what the model can do, right? So either way. So there we go. Woo! There you go. You made your first model in AI ECF. Yay! Yay! Was that easy? Yeah, very easy money. Extremely difficult. Oh yeah, totally, yeah. All right, and say we want to predict for a single point, right? So if we do regress.predict, and we give it some type of point, there we go. We get our outputs, and this is 8.25, right? And if we look up here, 8.25. It's not necessarily the number we do have there, but it's pretty close, right? Close enough where we say it's a pretty good guess. So, yes.
What's the shortcut you're doing to run each?
So if you guys want to run the code, you can either click the little play button up here to run it, or you can do Shift Enter. Shift Enter is an easy way just to run through them right quick. Yes. Any other questions right quick? Okay. So yeah, there we go. So before we get into a more complex data set, just want to take a moment to talk about it. So the Ames is a city that had a bunch of data about housing, and they wanted to see if data scientists could do some cool stuff about it, right? This was collected between 2006 and 2011, and it's a fairly sized database. Data set, I should say. So we contain about the clean version of this data set, so the one that doesn't have a lot of noise to it, and it's something that we're going to be using today, has 2,930 observations in it, with 80 predictive variables. The original data set had 3,970, but they're a bit dirty, so we're going to be using the clean version because we don't want to sit here all day and do data cleaning. All right? So we got that. And we want to know what's inside, right? Yes?
What does it mean by predictive variables?
Okay, so we take our x and we send it through the model. We're using our x to predict stuff. So when we say predicting variables, it just means our x. Right. Fair?
So you just did it eight times.
Yeah, you just in this data set we have 80 x's instead of 1. Right? And you can do, if you have more variables, you can probably get a little more nuanced model in there, right? But we'll go see that in a second here. So in this data set, we have a few different predictive variables. We just don't have something simple, right? Because it's never something simple. So we have continuous variables. So continuous, they go from 0 to whatever, or negative numbers sometimes. And we have stuff like garage area, wood deck area, pool area, if they have a pool. You know, some of these variables can be 0. You know, you can live in a house that doesn't have a pool or a deck. It's a sad existence, but yes, you can live like that. You have some discrete variables. So basically stuff that happened at one time, right? So stuff like remodel dates, you know, the date it was made, years sold. And then we have some nominal and ordinal variables. Nominal is kind of like a scaling factor, right? So you can say that a kitchen is in good quality, okay quality, bad quality, right? You can say that the house is well kept or falling apart, right? You can obviously see that there's a difference in quality from the badly kept place, the goodly kept place, right? And then the ordinal stuff, that is going to be the variables where there's not an obvious scaling factor to it, right? So you can have wood floors at home, you have tile floors at home, you have, you know, vinyl floors at home. They're not really like better than one another. They're just different floor types, right? So those are nominal and ordinal. So we have 23 nominal and 23 ordinal, right? So here's some questions we have, right? We want to know if there's some type of linear relationship between the above ground living area. So it's all the space above a basement. I know you guys are from Florida, but basements are stuff below ground. So above ground living area, right? And we want to see if we can possibly use that variable to predict house prices, right? Do you guys probably think there's something that could happen there? Right? Maybe if we have a bigger house, it's going to go for more. Right? Probably generally, right? If I have like a little shed in the back of my yard, it might go for like, you know, a tenner. If I have a big mansion, you know, I might get like something a little more decent off of that, right? So we're going to be looking at that. So to do that, we're going to be inputting our data. And so we input our data, we're going to get the mean, the variation, or the variance. So how much kind of like, I don't want to say error we have on it, but how much one point would differ from another point. That's what variance would look at. Median, and then skew. So skew is how much our data is to one side or another. A way to think about that, how many mansions are in Orlando in comparison to regular size houses? There's probably a very few mansions and a lot of just regular houses in Orlando, right? So we can say that the housing stock in Orlando is probably skewed a little more towards the smaller residential houses. We'd say that. So that's kind of what we're measuring here with skew. And we get all those variables right down here. Beautiful. So we can view our data using something called a box and whisker plot. There we go. So here's a way to kind of interpret what we're seeing here, right? This line right here, that's our mean, right? So middle of value, it's kind of low, right? And about 50% of everything exists in this little box right here. And everything out here, they're a little farther away from the mean, but they're still kind of within a relative distance from the mean. So not too far away. And all this stuff up here, we would consider our outliers, right? You guys see there's quite a few outliers in this data set, right? It's probably all those mansions in Ames, right? So, go down. And let's just do a simple little scatter plot of our data, right? Simple little scatter, so each of these points is a different data point. and then we just plot it, right? So we got sales price up here. This is going to be above ground living space, right? Does anyone see a nice little trend there? Maybe? Yeah? Does anyone see a possible problem with this data? Variance is not constant. Exactly, right? So we have a nice little cluster of stuff right down here, right? But when housing, when the above ground living area really goes up, you see that we have a few houses that are very well priced. Then down here we have some very big houses but with low prices. What do we think could be happening there with those houses?
They're in serious disrepair.
Okay, could be serious disrepair. Foreclosure, right? If you go short sell something, you know, you get a pretty good price on it. Anyone else?
Haunted.
Haunted, yeah. Yeah, who wants to buy a haunted house? Yeah, yeah. The only house I can afford. It's okay. So yeah, it could be a haunted house. You know, it could be that the Mystery Incorporated, whoever did Scooby-Doo, right? Scooby-Doo never visited these houses, so that's why the price is down low. So could be a lot of reasons. Until we look at the other variables, it'll be kind of hard to determine, right? But for the meantime, we can say there's definitely something funky going on here. And probably something a little less funky going on here, right? They look pretty reasonable, like, yeah, a very big house for a high price. Who would have thought? Crazy idea. Right? So, let's go generate our model. So just as before, we're going to be using a linear regression. And we're going to fit to intercept. This is just one of those hyperparameters we can tune here. And we do model.fit. We're going to do price predict equals model.predict. So that's what Mark was referring to earlier here, right? We're going to be using our actual model to predict these things. And then we're going to put all this on a scatter plot to see how well our model does. Oh, look at that. Now, does anyone see any problem with this model? Anyone? Now, here's something I would say. Maybe down here, the model works pretty well, right? But then over here, we see the model kind of falls apart, right? Yes?
The variance isn't constant?
The variance isn't constant, yeah? So over here, the variance is pretty close together. Then out here, you have a really big increase in variance. So right around here, our model breaks down, like, it predicts no values past this point, you know? It could predict these if it was skewed a little more upwards. Maybe if we had a different regression line, so maybe something a little more curved. Maybe if we got rid of some of these outliers down here, we can have a better model too, right? Because if we did include haunted houses in our data set, you know, might make this data model a little better. But either way, there is our model. Yay! So yeah, pretty easy. And now we're going to be applying logistic regression. To do that, we are going to be importing a new model from Scikitlearn, and this is going to be logistic regression. So yeah, we don't have to do any crazy maths, right? We can just import the logistic regression model. Then we're also going to be importing this thing called the test train split. Now, where do you guys think we'll be using test train split in? Anyone? Yes.
Train, test, and split the data.
Yeah, basically, right? So you guys remember that during the lecture, we want to have a set of data that we could use to test whether or not our model's doing well. And we take that data and don't train on it, right? So we have this data that's being unused for training, and we're going to be using that to make sure that we don't overfit our data, right? To make sure that stuff generalizes pretty well, right? So that's what we're going to be using that for. Oops. So in this data set, we are going to be using something called the adult data set. It's census income, right? So we have, every 10 years we have a census, right? And the census is coming up soon, so make sure you guys fill out that census forms when they come in. And basically they took a bunch of census data and try to see if there's some correlation between a bunch of different variables, right? So, I'm going to print some info right down here. So this is what our data set looks like, right? We have 32,000 just about data points in this. We have integers, and we also have these objects. When you see objects, you can pretty much be certain that the object is going to be a string. So we have some words to describe what class, occupation, relationship, race, sex, and all that, right? So, let's go down here a little more. When we do data.head in a PD's array, we can actually show what our data, well, the first 5 entries of our data is, right? So we can see down here that we have 39-year-olds that work in the state government, have a bachelor's, an education number, and education. These relate, right? So if you have a bachelor's, education number will be 13. If you're a high school grad, your education number will be 9. If you only have a part of high school, 7, so on, right? If you have a PhD, it's going to be up there too. Marital status, pretty easy, married, not married, single, divorced. Occupation, relationship, white, so race, sex. Capital gain. Does anyone know what capital gain is? Yes.
It's the money you make on Bitcoin.
You don't make money off Bitcoin. But money made off of investments, right? And Bitcoin's not an investment. Okay. I didn't say that.
Tell the IRS that.
Well, Bitcoin's more of a capital loss.
Oh.
What will capital loss be?
Depends on, what time period you're talking about.
Right now. It's
Yeah,
this.
right now.
Yeah, it's right now it's this. Maybe 5 years ago, different story, but right now, we're definitely that. But capital loss, opposite of capital gain, right? So the money you lose from investments, right? So say 1 year you made a bunch of money off of Bitcoin, had a really big capital gain, IRS took a bunch of money from you. Next year you had a really big loss from Bitcoin. It's okay because you can deduct all that from taxes, just so you know. It's not, you won't be crying, if you have a bunch of stuff you deduct. Then hours per week, so that's how much you work, right? So we see here, someone down here, they work part-time, and all these other people here, they work full-time. And then native country, so where they're from. We see quite a few of these people here, they're from the States, and then someone down here is from Cuba. And then this right here, income, this is what we're trying to predict, right? So 50K is kind of the cutoff we're going to be using here. So we want to find out whether or not someone makes more than 50K in a year or less than 50K in a year. Is that pretty reasonable, right? And we have all these different variables that we can look to, right? And if you want to find out a little more about our continuous variables, get you out of the way, right? We can do data.describe. And this will give us some of our statistical stuff we want to find out about these different variables here. So the only continuous data we have here will be age, final weight. So final weight is basically the proportion of the population that belongs to this class, right? Education number. So, how educated are they? Capital gain, capital loss, and then hours per week. Right. So now, here's the fun part. We have this little thing here. See this array is not implemented error? If I try to run this right now, it's going to fail because I haven't written anything there. So your task right now, it's very simple, is to basically define what we should have as our test variable. Right? So which of these continuous variables, because with logistic regression, right, we need a continuous variable, right? So we need to decide which of these continuous variables we want to use to make the best model possible. And to do that, all you need to do here is say test, test equals, and then put the name of the class you want to predict against, right? So if I would want to predict against age, all I have to do is write age, run it, and then I'll make up my model. And there we go. And then I won't print out the score because this is something you should actually test out. So give yourself a minute, just kind of go through the whole, go through it, find out which different thing you want to look at to see whether or not someone will make more than 50 or less than 50K a year, right?
If you need any help,
Of course, yeah. Mhm.
You want to print it out. Just like print your variable. Or put them in the table and test it.
Howard didn't run.
It's not obvious how you print it, test it, what?
So if you go down
Yeah,
here,
you gotta run them in order. It's like code is order down the clock. So top down.
yeah. So
Yeah,
go down here,
but it has to be.
we set our x to whatever the
like
variable
a-
is.
Yeah, so you can put like age or
So you just have to have test equals and then the string of whatever next to it. So it's not completely obvious, which is kind of why we have to explain it a bit.
So here's this final way,
So the
what
group,
is this group?
so final weight, what is it good? In this group, so every person belongs to.
Mhm. What are you doing?
Cause like, it
So
could be like,
here you
they're all
want to find
different.
test.
Yes.
You
Well,
want to
it's not saying,
raise the
it's,
touch?
Yeah,
Or just
if
this
you have
specific
that, it's
combination.
gonna.
no, so this group means
So you want to find test.
this
Yeah.
entire sample, this set
It has to be
of people.
a string.
Because remember, our data is only a subset of the
from the
population,
continuous
like all
variables?
the people that we're trying to look at. So final weight describes this sample of the people that we have right now, this data that we have right now.
Okay.
Does that make sense?
Yeah.
Kind of.
That.
So, so we
so
have
not
like what,
income, though.
30,000
Income's
people that
the
we have
objective
data for,
variable,
right? Well, the actual
It just has to be
population
a
could be a
string
couple
itself.
hundred
It-
thousand people.
So it
Yeah.
either raise
So
final weight,
final
education,
weight,
capital
when it's saying
gain
this group
plus
means this 30,000
week.
people that we have data for.
Then why does it have different,
Because
It can't be from there. It just has to be the.
because each person
string
is
itself.
part of a different, so that's like the sub.
It has to be the
that's like
string
the
itself,
overall
not from
group.
within
Each person
the-
is also under
the
the
array.
subgroup based on like all the other stuff. Okay, so I think that's what.
So you just have to put down the string
so,
of final gain.
so it's a combination of the other things. Yeah,
And
sorry, I
then-
misunderstood what you're saying. Yeah.
Okay, cool.
So some people have similar. It's like some people. There's multiple people that bachelors.
Okay,
So there's kind of groups that we kind
Just do this.
of like.
Yeah, so
divide
you
them
see
up
up
like
here,
that.
text
Okay,
equals
thanks.
age. That's all you need to do to make it right.
Mhm.
Yeah.
Now, are you interested in improvement?
Not necessarily improvement, just see which of these variables will make the best.
I'm talking about a couple additions to your.
Oh yeah, sure, of course.
All right, so this is your code.
Because sometimes,
All right,
it says
this is all done by hand.
Mhm.
Caught out there by hand. So one of the problems I see with this is that it's not a problem, it's just something's not very clear.
Mhm.
And that is you defined
so you need to,
Here,
you have to remove this race
your
up
line
right there.
to be the vector,
That raises
the average of x across the average of y.
Mhm.
So you just have to.
That assumes an origin of 0.
Yes.
Okay?
Oh,
And that's
yeah,
not
yeah,
necessarily the way the line would actually be. Okay? So that's not all quite obvious in here.
Yeah, so that's where you guys are having issues with.
And of course, you get your
Oh, sorry,
coefficient
yeah.
approach within 0.
Mhm.
Or whatever, based on how you define it.
Yeah, so you gotta pull up your own.
All right, so after you do your regression
You're gonna have to create your own account.
okay, it's real simple to grab the coefficient, let's look that up. That's all you gotta do is grab this coefficient from the model.
Mhm.
So there's the regress dot intercept and regress dot coefficient.
Mhm. And they're different.
They're different.
Yeah.
And now what's very interesting is just do that plot again, but add the model into the hand. So the blue line is the hand fit we did, which is the 0 origin.
Yeah.
The green line is the model fit, which the origin is not 0, it's slightly above. And it's a little closer overall.
Yeah.
Now, it'd be interesting to put the different standard deviations or whatever between the two, but I think that extra plot gives people the clue to show them, because you describe them as we don't ever need to do that. When Scikit doesn't offer it,
Yeah.
it's fine, we just show it's not included.
Uh,
All of our plots go to like hands.
Mhm.
So all it takes is a couple of lines and you can show
Do you guys
I
do
have
this?
What was this
homework,
type of?
I've
So you want to delete that line.
It's only just
been
a
predicted
in the room.
based
I
off
kind of
of
placed all this code, I only had one line there.
Yeah.
So you just want to write up what he has up there. He says
And I
test
showed
here.
right here, 2 lines how to extract.
The
Okay,
three
so you're
values.
just
Slope from the one
Capital law.
from
Okay.
my mom.
Okay.
So just those couple of
So-
things, I was able to help nicely. Give you, here's the line, here's how easy it is.
Test is a variable.
Okay.
So when you, so to define a variable, you don't need to do anything like, it's not like Syria and, or you can't,
Oh,
but
definitely.
you just declare it like that, and to declare a
Of course,
function
of
with
course.
that,
Well, if you submit this notebook, I think we can see all the submitted notebooks and the
that and then
competition.
conditions you do,
Yeah.
you do like if,
Actually, let me.
Yeah, that's what it said.
Well, I don't want to submit all my environment stuff at the top. That's just stuff I like to figure
I'll
out.
just come with that.
Oh, shit, and what's interesting in the diagram is I'm running it Ruby too.
Really? Well, it's probably done within a VM.
I got GCC compiler, shell access to root, and it really runs any program I want.
So that's also.
You gonna break Kaggle now?
No, I'm just saying, I just found it interesting, there's zero security. They really give you a VM
Yeah, I don't know.
for $6 per tab. GPU says it's only $8. That's access, access to compilation tools and everything.
I'm just giving you that basic.
So GCC is on here.
No, so that's all configured. So if I do this,
Oh, that's a security
this is,
vulnerability.
Well, I mean, most times, let me go back.
that just, it's spitting out some stuff, but it's really not doing anything. It's just declaring a hash. So,
GCC,
Yeah, or just.
GCC,
Yeah.
dash, version.
so,
Oh
yeah,
my
so,
God.
And I'm logged in as root, so if I do this, for instance, watch.
yeah, so what this is gonna do is
Touch,
the income is less than $50,000, so it's gonna output a 0. Otherwise, it's gonna output a 1. So it's gonna be, I think we're giving more than
test,
$50,000.
C.
So that would be like our binary output. Income fixture, that's just the name of the function that we're doing. So, let's go check out our data. So,
See,
uh,
I created a root clone file, I'm running it, I can echo stop doing it. Actually, let me just do a compile,
So you can basically take the hot
Anybody
book,
else having any issues?
dump it into a text file, compile it, and run it on the machine, then compromise
So
it.
I know
I
a
wanna
few of
see
you
if any more-
are leaving. So just remember for the feedback
so
form.
now-
Yeah. Just remember to fill out the feedback form. That again, that really helps us.
either greater than
What are, so I'm curious, what are some results you guys,
So now
you guys
just
getting
go
any type of accuracy?
1 or 0. If you can see.
You got errors?
Yeah.
That's okay.
Yeah.
So we'll work through
Yeah,
them.
so
Yeah.
now it's in terms of what we're
Got
doing.
0.8%.
That is
Alright,
kind of
nice.
what this.
So capital gains, you got any? Yeah, so capital gains,
That is, we're editing that.
seems to, you don't wanna like get, you
And then
know,
what we're doing is calling that
highest
function.
accuracy, which kind
That's
of
like
makes
pretty
sense,
tricky to
because, you know, the more capital gains you have, probably
But
the
that just
higher.
fixes that
You know.
income.
I would try all the other variables and see, yeah.
So you ran
And if you guys are having issues
can
where
add-
you try one variable and it works, but you try another variable, it
I think
doesn't,
you have to-
it raises an error, just run through, all of the cells,
So
I
this is
guess, so
logistic
the data
regression.
cells, which I can come over and help with, but it's just a Kaggle thing that
Okay.
I didn't realize beforehand that was happening. It messes up the data if you try to run it.
I figured out that if you click run all.
Yeah, so run all, you can also click run all to run all the cells, or you only need to run the cells
Probably
that
run like
pertain
version
to
of
what you're,
that,
just with the data set you're using. But you can, or you can run all of them, so it doesn't-
It's just easier to click what I had to do before.
Yeah. So you can just click run off, if you're getting errors or something, when it should be working, just click run off, and that can definitely help. So, anybody else having issues?
Well, that's why I was familiar with zero.
What? Okay, alright, cool.
Okay, so.
Yeah.
It's-
Yeah, see, it's that, yeah, I think that's looking like it's gonna be, the best result, but.
So Kaggle comes equipped with the GCC compiler, and you can run C programs in Kaggle.
Specific columns.
Well, yeah, 'cause
On
you
the
get,
machine.
you get a Linux thing, so
Just
you get
test
GCC,
that
and
against
you
the
LS.
But your users also root.
Do you follow that?
Well, yeah, it's like a
So we can, we're just using that
No,
variable
but if you
to
can
grab
run
that
C program, you can run
this variable for education, and then our x is now going to be education.
I mean,
instead of-
possible. I'm sure they.
But for now, we're just going to use
Why do you have the developer console?
age.
because I
So we're
pressed
using
button.
age for income set by.
Do you have anything else you want to say?
I can run the rainbow
This,
train.
yeah, this is just.
Will you run the rainbow train?
What?
The rainbow train.
Yeah, and then.
So, there's also the. I can talk about the Kaggle competition. All right. So, can I get your guys' attention? Can I get everyone's attention? So it seems like 80% was about what some people were getting, and what was the parameter you're using to get about 80% capital gains? Right. So that seems like, the more money you make for your gains, you're probably going to have a higher income. So makes sense. So you're able to predict that. So there's one last thing that I wanted to cover that we're setting up that we did last semester, but I just wanted to go over again, which is the competitions. So I just create a small, for most of these projects that we're going to be doing, I create a small competition so you can submit to the competition and basically you can view like your results compared to other people. So here kind of all our models are pretty much the same and we're just trying different parameters. So the results will be the same, but it's just an introduction so you know how to like the submitting process. But later on you'll have the ability to be able to try your own models and try to get the highest percentage and submit to the competition and see how you compare to other people. So it's just a little fun, friendly competition. So this block cell at the bottom will, if you run this will pretty much take whatever model you have and create a submission file for it. And so the submit, I can go over how to submit in a second. Does everybody was able to run this code with no errors? So they got their submission. This last block, thumbs up. Good.
Not
Great.
here.
All right. What?
Yeah, not here. What was it?
Okay. So once you do that, in order to submit, we're going to have to click the commit button up here, which pretty much this commit button saves the state of your notebook. So when you're editing it, it's called a draft on Kaggle. And when you commit, it kind of makes like a final draft and it saves like the state of your notebook that you have now. So you can give it publish it to other people and give it to other people. It's already a fully ran notebook with all the output and stuff. So as you can see here, you click commit and then it's gonna take a minute and do its thing and run. And then once it's done, does everybody commit and got it up? Good. Back there. Good. Okay. So we'll click open version here. And then this will open up our final version, and this is where we can submit. So this is our final version of our of whatever notebook you've created with all your edits and stuff. And so down here, if you go to output, so on the sidebar here, you have notebook data output. You'll see the submission file. So all you got to do is just click submit the competition, and then I'll submit for you. And once you do that, you can go view the competition and view the results from other people. Everybody's able to submit the competition? Good. Thumbs up or nodded heads? Make sure everybody's good? Okay. You're having issues? I can come over and help. But all right, so, and another thing, 'cause I know we're packing up and leaving. Again, I know I said this like 8 times, but one more time, feedback form, please. We always need your feedback and stuff.
Helps us do better in the future.
Right. And also, I just wanted to say, thank you. Thank you to Jarvis for doing the notebook. And, thank you guys for all coming out to our first meeting. So we got a lot in store this semester, so I hope to see you guys. There's another thing we'll be starting next week too. So next week we'll be starting office hours. So I think we have it for almost every day during the school week. We have all different times. We'll have coordinators in Discord over voice and over chat, text chat. They'll just be hanging out for an hour, so you can go then and ask some questions about whatever was covered, or if you have some other questions, or you're like, hey, I need some help real quick with this code. I wouldn't go with extensive coding problems because again, there's only an hour. But if you need any help with anything really, you can come and ask the coordinators there. So, and different people are giving that out every week. Yes.
All of the office hours are posted on our calendar.
That too. Yeah. So we have it our calendar. So if you go to ucfai.org/calendar, that'll have the calendar for all of our events and meetings and stuff, and also the office hours. So there also will be posted in Discord today after the meeting here, so you have the times there as well. So any questions or anything, or yes?
Also, if we miss any of the presentation, like we're coming late, because it was a good presentation beforehand, talking about linear regression. It came in a little late.
That's fine.
Do you have them available on your main website?
So our website is currently down. Hopefully get that up today, but I'll be posting in the Discord the slides and stuff. We also, as you can see, we're recording, so we'll have the full recording, so you'll be able to view the recording as well to get that first part missed. I'll also post the slides, so you have the slides and the notebooks available online, so you can view that too. So yeah.
This will also be located on the website.
Yeah, so we'll be located on Discord, and then when the website up, you'll see a lot of announcements that the website's up, and then everything will be available through the website. Yeah. Yep. So we still have 25 minutes because we have the room till 7:30. So if you want to hang out and just continue working or talk to any of the coordinators or anything, feel free. Otherwise, thank you guys for coming and have a good night. Justin, did you have something you want to? Okay.
Thank you so much.
Yeah, thank you guys.
Thank you.
Give a clap to Jarvis. Jarvis is clapping. He doesn't even know we're clapping. All right, thank you guys. All right, let me stop the recording. I think, did he stop it already?
No. Yeah.